In this video, we're gonna work on a related rates problem using inverse trigonometric functions. Here's the problem. A ship moving at a constant speed of 8 miles per hour sails north for 30 minutes and then turns east. If a searchlight at the point of departure follows the ship, how fast is the light rotating 2 hours after the start? Let's say this is the point of departure. This is also where the searchlight is located. The ship sailed north for 30 minutes. So he covered a distance of 8 miles per hour times 30 minutes. So that would be 0.5 hours. Okay, so 0.5 times 8 miles per hour. This is 4 miles, right? He turned east after 30 minutes, right? And then the searchlight is following its movement. So we can draw a line here from the searchlight to this arbitrary point here. Okay. So this is a right triangle. This quantity is unknown and this will change over time, right? So let's call it x. And then another quantity at play here is this angle here. Okay. Alright, we know that the ship is moving at a constant speed of 8 miles per hour. Therefore, this quantity here, x, is changing or increasing over time with the same rate as the speed of the ship, right? So that would be 8 miles per hour. The question is how fast the light is rotating. Basically, we want to determine the change in angle theta with respect to time. Okay, so that would be d theta dt. 2 hours after the start. So d theta dt, 2 hours after the start. Okay. Now let's set up the working equation. So we have here theta relative to angle theta. This side, which is measured to be 4 miles, is the adjacent side. And then x here is the opposite side. So opposite, adjacent, we can use tangent theta, right? Tangent theta equals opposite over adjacent. Opposite side again is x. Adjacent side is 4 miles. Okay. Now, there are two ways we can differentiate this equation. Okay. We can use the trigo function approach or the inverse trigo function approach. Let's try the trigonometric function approach. Okay, so differentiate this equation with respect to time implicitly. Tangent, its derivative is secant squared, right, of theta times d theta dt equals, we have here a derivative of x over 4 with respect to time. So we get 1/4 dx dt. Now let's differentiate using inverse trigo. Okay, so first we need to isolate theta. So take the inverse tangent of both sides. This results to theta equals arc tangent of x over 4. Taking the derivative with respect to time, this gives us d theta dt equals derivative of arc tangent is in the form 1 divided by 1 plus the square of the argument, in this case x over 4. So we get x squared over 16, right? And then derivative of x over 4 with respect to time. So that would be 1/4 dx dt. Okay. So again, we have two ways to solve the problem. The question now is which of the two is the better option. Now, if an angle measurement is given, so if theta is given, for example, as part of the known quantities or part of the condition, okay, then we use the trig function approach, okay, because we can easily evaluate its trig function value. If it's not given, then we cannot immediately solve for its trig function value, in this case, secant of theta, or 1 over cosine of theta, because secant is the reciprocal of cosine, right? We still need to find this quantity here so that we can determine the value of secant theta, right? Because secant theta is hypotenuse over the adjacent side. Okay, so basically it needs additional work, okay, before we can solve for whatever is required in the problem. That's why we have the option of using inverse trig function. The catch, however, of using inverse trigonometric functions obviously is that you have to know the formula of the derivative. Okay? At least you have an option, right? So you just choose between the two approaches. So you try the trig function approach on your own. Let's continue solving using the inverse trig function approach. Now let's check if the quantities involved in this equation are given or known so that we can solve for d theta dt. Okay, so let's start with x. Do we know x? We don't know x yet, but we can solve for x later on. Okay, how about dx dt? It's given in the problem 8 miles per hour. All right, so our only problem now is x. Let's solve for x first. Solve for x using the given condition 2 hours after the start. Okay, so 2 hours after the start. If we read the problem again, it is stated here that he already sailed going north for 30 minutes. Okay, therefore the time for its eastward travel is 2 hours minus 30 minutes, right? And that's 1.5 hours. Okay, so to solve for x is equal to the speed of the ship, so that's 8 miles per hour, times the time. So again, the time is 1.5 hours. Okay, so 8 times 1.5, x is equal to 12 miles. Now let's plug in the values of x and dx dt into this equation. Okay, remember x is 12 miles and dx dt is equal to 8 miles per hour. Okay, so we have d theta dt equals 1 over 1 plus x squared, where x is 12, so 12 squared, that's 144 divided by 16 times 1/4 times dx dt, where dx dt is 8 miles per hour. So times 8. Okay. Simplifying, we get 1 over 1 plus 144 over 16, that's 9. And then 1/4 times 8, that is 2. Okay. Simplifying further, we get d theta dt equals, we have here 2 divided by 1 plus 9 is 10. Therefore, d theta dt is 1 over 5. and the unit is radians per hour. This value as a whole represents the rate at which the searchlight is rotating 2 hours after the start. So this is now the final answer.